topic is about, as you can see, it is about something which as prerequisite needs these definitions, which I discussed in class 6, and the discussion was about movement about origin, and movement about mean. The note which is in front of you, probably all of you can see, this was the formula of movement about origin, and where you see that I wrote this. Please mute yourself. Please mute yourself. Please mute yourself. Okay, so this is the formula which I was actually discussing in class 6, and this formula was about movement about origin, and you see the expression, it is expectation of capital X to the power R, and which we define as mu R prime. When capital X is discrete, this mu R prime is defined as summation X to the power R multiplied their corresponding probability mass function. And when capital X is continuous, mu R prime is defined as integration from minus infinity to plus infinity of the integrand X to the power R multiplied by its corresponding probability mass function. That was the thing which I discussed in class 6 in the chapter of movement. Now, all of you, I shall ask all of you to note down this particular formula in your copy right now, because I'm going to scroll down. Okay. So my today's topic is actually this one, module 4. I'm starting module 4, and this topic, the first topic of module 4, as if you can see in the syllabus, it is about probability distribution. It was not about actually probability distribution. The first topic was written as skewness and kurtosis, but I decided to discuss probability distribution discrete cases first. And you can see that in the syllabus it is written, we are supposed to evaluate the statistical parameters of Poisson and binomial distribution. And if I talk about the statistical parameters of this distribution, then you very well know that binomial distribution is having two different parameters. One is the number of experiment, and another is the probability of success. And Poisson distribution has only one parameter, which we define by lambda. So here we are going to evaluate the nature of these. We are going to evaluate the parameters itself from the distribution. Okay, I'm going to show you how to evaluate these statistical parameters for Poisson and binomial distribution, and what mathematical tool is needed. This is a very important topic, so you be concentrate, be attentive. My definition, my today's very important definition is about the moment generating function. It's a very important definition. All of you can see what I have written over here. The moment generating function of the random variable capital X is defined in the following way. We denote the moment generating function of the random variable capital X as mxt, and this is implied by expectation of e to the power t into capital X. Okay, what is t? T represents actually the time. Okay, t represents time, but we shall not discuss about the nature of t here, because actually this moment generating function is very important in Markov analysis, and Markov analysis is actually needed in signal and systems. I have seen the book of signal and system, and these things are there. Now, but we shall, for the time being, we shall treat the variable small t as just a variable. Okay, so moment generating function of the random variable will be denoted by this notation, and will be defined as summation over x, all possible values of the random variable capital X. Summation will be taken over e to the power tx into fx. Fx is the probability mass function if capital X is discrete. And as usual, the moment generating function of the random variable which is continuous will be denoted by, when we replace summation by integration, and integration is taken over all the real lines, the entire real line. This is the definition of moment generating function. Secondly, I must remind you this particular series. This series is very well-known series. We have done it several times in your earlier courses. It is the series of e to the power x. And in place of x, we have tx. So all the x's have been replaced by tx. You see, 1 plus tx whole square by 2 factorial plus tx whole cube by 3 factorial plus dot 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 plus tx whole to the power r by r factorial plus dot dot dot. R is positive. Now, this e to the power tx has been shown over here because e to the power tx as a function or as an integrand is present here in the definition of moment generating function. What changes, e to the power tx will always remain, but what changes is we change the probability mass function or probability, we choose probability mass function or probability density function accordingly as the nature of the random variable is. Okay. And one important theorem which I have mentioned over here is this. The derivation of the theorem is not there in the syllabus, but you have to recall its definition. You have to remember you have to memorize its result. It is saying that if we have a moment generating function of the form mxt, and if we take the rth derivative of the function with respect to time t, and if we put t equal to 0, then the result which is obtained is similar to mu r prime. Mu r prime is defined in class 6, which I showed you in the beginning of this session. So mu r prime is expectation of capital X to the power r is also same as this formula. If we take the derivative of the moment generating function, mu r prime is also obtained. Okay, so we are going to connect all these different things together to get something out of it. First of all, we shall consider the discrete case. Okay, so discrete case actually, for discrete case, what actually happens is that, so we have got the series of e to the power tx. We shall replace the series over here in place of e to the power tx, as you can see. And we will operate the sum on each of these terms. Okay, so summation will be operated on 1 into fx, that is fx. Summation will be operated on x into fx. Summation will be operated on x square into fx. Summation will be operated on x cube fx. Summation will be operated on x to the power r into fx, and so on. And what about these coefficients which represent time here? The coefficients t square by 2 factorial, t cube by 3 factorial, t to the power r by r factorial, these coefficients are actually constants, and constants can be taken outside the summation sign. So if we do so, you see, by our previous result, we can say that we know that summation x fx is what? Expectation of capital X. Expectation of capital X can be written as expectation of capital X to the power 1, and that is same as mu1 prime. Similarly, expectation of x square, this is expectation of x square, that will be mu2 prime. Expectation of x cube, that will be mu3 prime. Expectation of x to the power r, that will be mu r prime. And t square by 2 factorial, t3 by t cube by 3 factorial, t to the power r by r factorial, they will remain same. That will not be affected by anything. And also you know that mu is equal to mu1 prime. How do I know this? I have written here, you see. Somewhere I have written. Okay, probably below. Let me finish this particular section first. This mu equals to mu1 prime means if you go through the note of class 6, you will find that mu1 prime is the first moment about origin, and first moment about origin is summation x into p fx. Summation x into fx can also be written as expectation of capital X, and expectation of capital X is represented by mu in statistics universally. So we can represent mu1 prime as mu. So I have replaced mu1 prime by mu over here. The entire thing can be, and the entire calculation shown over here can be repeated if I replace capital X, which is discrete, by a capital X, which is continuous. Then everything will remain same. Everything which is in front of you on the screen will remain same, but all the summations will be replaced by integration. Okay, so all the summations will be replaced by integration, and so the ultimate result will remain same. So mxt has this particular form. Okay, that will happen for continuous case. I have not shown here, I have not shown the explicitly what will come in the continuous case because they are similar, but only I have written here as a note that if the case is continuous, all the summations will be replaced by integration. Now, after learning this moment generating function, how is it applied in statistics? How is it applied in different statistical distributions? So first of all, we have considered the Poisson distribution, and we are going to find the moment generating function for the Poisson distribution. We know that Poisson variate is a discrete variate, and since Poisson variate is discrete variate, its probability mass function is defined as this. This is the probability mass function of Poisson variate. Now, according to the definition, the moment generating function of the Poisson variate will be mxt, expectation of e to the power t capital X. And that will be defined as, by definition, which I have discussed above, will be summation x, because capital X Poisson variate is discrete, summation x e to the power tx, and fx will be replaced by Poisson variate's probability mass function. Then e to the power minus lambda is constant. That will be taken outside the summation sign. And you see that lambda and e to the power t, both of them have been raised to power x. So by the theory of exponent, lambda to the power x into e to the power tx can be represented as lambda into e to the power t whole thing into the power x by x factorial, where x runs from 0, 1 to up to infinity. That is the domain of the Poisson variate. We all know that. In the next line, what I have done, I have replaced this general small x by showing its limits explicitly from x equal to 0 to infinity. Okay, so we have got this. From your first semester course, you already know, your first year course, you already know that this type of function, summation x from 0 to infinity z to the power x by x factorial, this function can be categorized as a Maclaurin series of e to the power z. So you see, if I compare these two functions, this one and that one, in place of z, we have lambda into e to the power t. So summation x from 0 to infinity, lambda into e to the power t whole to the power x by x factorial is the Maclaurin series of what? If this is the Maclaurin series of e to the power z, this is the Maclaurin series of e to the power lambda into e to the power t. Okay, just compare. Just compare these blue colored sections. Now, mxt can be replaced as, mxt will be e to the power minus lambda, and the entire section will be replaced by e to the power lambda into e to the power t. So that will be written as e to the power, take minus lambda common, we will get 1 minus e to the power t. And if this minus sign is irritating you, you can put it inside and we can write it as e to the power lambda whole thing into e to the power t minus 1. We are naming it as equation 1, and that is the form of the moment generating function of the Poisson variate. Unfortunately, you are going to memorize this particular formula, and you have to memorize this particular formula. Nobody can help you. You have to memorize. This is the formula. Now you will see, you will ask me that, so why did you find this moment generating function of Poisson variate? What is, why? What is the reason? The reason is, now you see, we are going to differentiate this moment generating function with respect to t once. And if we do so, and you are pretty much well versed with how to differentiate a particular function, I'm not going to say the details of this differentiation. We are going to differentiate mxt with respect to t once. So we are representing this as mxt dash, and that will, this particular expression, after differentiating with respect to t, this particular expression will come. You can verify by yourself. Okay, if you have any doubt in your mind, you can verify. And again, we are differentiating this for the second time, and we are representing this as mx double dash t. That is the double derivative of this expression. And if I do this, I will get this huge expression after the differentiation of the first derivative with respect to t once again. So these are two derivatives which I have obtained from the moment generating function of the Poisson variate. I am naming these two derivatives as 2. Now let us apply this theorem. What was the theorem? Let me show you the page once again. The theorem said, if you take the derivative of the moment generating function, if you put t equal to 0, you get mu r prime. Okay, so we are now going to apply this theorem over here. Oh, here I have written, see, for your information, that when r equal to 0, mu 0 prime is 1, and when r equal to 1, mu 1 prime is expectation of x, which is mu actually. Now, if I take, since I have already differentiated mxt with respect to t, now in place of t means time. In place of time, I am putting 0. And mxt at the value t equal to 0 will be, you substitute t over here, you will get e to the power lambda. E to the power 0 means 1, 1 minus 1 is 0, so that section will be 0. And lambda will be there, and e to the power 0 is 1, so lambda will come out. So, and lambda, you know, it is expectation of capital X, and that is the mean of the Poisson-Variate. So first of all, we have derived the moment generating function of the Poisson-Variate, and out of that we have extracted out the mean of the Poisson-Variate. So we have evaluated one of the statistical parameter of the Poisson-Variate, that is mean. What is the other statistical parameter of the Poisson-Variate? Variance. We are going to derive it now. To derive variance, I am now going to apply the same theorem for mx double dash t. And I'm going to put t equal to 0 in the expression. And if you put t equal to 0 in this clumsy expansion, you will find that after simplification, you will get mx double dash at t equal to 0 will be lambda plus lambda square. And by theorem, mx double dash 0 is mu 2 prime. And mu 2 prime is nothing but is same as e of x square. Okay, by our discussion of class 6. So ex square has been obtained for Poisson-Variate. And we know that Vx is ex square minus ex whole square. Now you substitute. In place of ex square, I am putting lambda plus lambda square. In place of ex, I am putting lambda. Ex is getting squared, so I am getting lambda squared, and the difference will be lambda. So thus we have derived the second statistical parameter of the Poisson-Variate from the moment generating function. And we have seen that Poisson distribution is a kind of discrete distribution where mean and variance both have the same expression, which is the statistical parameter itself. I am going to now discuss the moment generating function of the binomial distribution. Okay. Now, similarly, if I am supposed to find the moment generating function of the binomial variate, I shall apply the same definition again, and this time the probability mass function of the binomial variate will be taken into consideration. So probability mass function of the binomial variate is ncx p to the power x 1 minus p whole to the power n minus x. 1 minus p can also be seen as q. Okay, so that will be ncx p to the power x q to the power n minus x. And the limit, the domain of binomial variate is restricted. The domain of Poisson-Variate was unrestricted. So I'm writing here x from 0, 1 to up to n. So when I'm replacing this, you see ncx remains same. P into e to the power t can be raised to the power x. Just look at the calculation. And q can be written as q to the power n minus x. And if you carefully observe at this expression, you will find that this expression is nothing but the general case, the general term of the expansion of q plus p e to the power t whole thing to the power n. If you use binomial expansion rule to this particular result, you will get this as the general term. So I have written here q plus p e to the power t whole thing to the power n. And unfortunately, students, you are going to memorize this result also. This result also is for the sake of the examination, you have to memorize. Okay, moment generating function for Poisson-Variate and moment generating function for binomial variate. So to find the moment you have already understood why moment generating function is needed. So to extract out the statistical parameters, I'm going to do the same thing. I'm going to repeat the same process for binomial variate now. So I'm going to take the derivative of this moment generating function with respect to t once first. and that will be n into q plus p e to the power t whole thing to the power n minus 1, p into e to the power t. Now I shall ask all of you to do the derivative by yourself, to check. Do not always trust me blindly. I am prone to mistakes. So you do it by yourself. And after this, if we substitute time t equal to 0, by the result, by the theorem discussed above, we will get mx dash 0 will be mu1 prime, and that will be n into q plus p whole thing to the power n minus 1 p. But q is the probability of failure and p is the probability of success. So q plus p will be 1. And therefore 1 to the power n minus 1 will be 1, and that will be n into p. And you know NP is the mean of the binomial variate. When I taught you mean, and when I wrote the results of mean and variance of the binomial variate and mean and variance of the Poisson variate in one of my earlier classes, I told you that I would be showing you the evaluation of these parameters later on. Now see, this is happening right now. My prediction is all correct. Now one statistical parameter has been extracted out. What is the other statistical parameter? That is variance. So I am differentiating the function once again, and I'm getting this expression. Okay, this clumsy expression once again. And at this expression, I'm putting t equal to 0. And if you do so, just like above, you are going to get this expression. Here again, I'm substituting q plus p as 1 in both these parts, and I'm getting n into n minus 1 p square plus np. That is e of x square. But what will be v of x? V of x will be the difference of ex square minus ex whole square, and that will be n into n minus 1 p square plus np minus np whole square. And if you simplify it, you will get np into 1 minus p, which is npq. And that is the variance of the binomial variate. So I have shown you how to extract out, how to evaluate the statistical parameters like mean and variance for the binomial distribution also, using the moment generating function of the distribution. Before I conclude my today's class, let me discuss another problem, which is not binomial, which is not Poisson, but which is something else, where moment generating function, the idea of moment generating function will be applied. I'm just showing you right now how to apply the moment generating function for unknown probability mass function or probability density function. This is a probability density function, fx equal to half into e to the power minus mod x. I don't know, and you don't know, this probability density function corresponds to which particular type of continuous random variable. The name of the random variable is not known to us. But it is, we can understand, since we are doing the chapters of probability, this is the probability density function of some continuous random variable. We are going to show that moment generating function of this random variable, associated random variable, which is capital X here, will be 1 by 1 minus t square. So by this example, actually, I'm trying to show you how powerful moment generating function is. And you can apply this moment generating functions idea in signal and system also, when you shall be dealing with different probability types of different varieties of signals, digital signals. Okay. Anyways, that is for later part. Let us keep it for separately. We shall be discussing later. Okay, let us concentrate on the problem. What is the function? The function is half e to the power minus mod x. Now mod x is here. So I'm going to show you the solution. You just follow the steps, how I am approaching the problem stepwise, because don't do the problems arbitrarily. Okay, always try to write the meaningful sentences and meaningful statements. So my first identification is, since mod x is present here, let us recall what mod x function is. Now the modulus function is defined as this. Mod x can be defined as x when x is greater than 0, 0 when x equal to 0, and minus x when x is less than 0. Therefore, the probability density function, it can be vivisected. Vivisected means I'm cutting. Just like we cut the frogs and snakes in the biology class, I'm cutting this particular function. Okay. So that's why I have written jokingly this word vivisected. So I am trying to actually write explicitly the function half into e to the power minus mod x. Now you see, if I apply this result over here, carefully observe, when x is lying between minus infinity to 0, that means x is negative, mod x is negative, mod x is minus x, so half e to the power minus mod x will be half e to the power minus minus x. When x is lying between 0 to infinity, that is x is positive, half of e to the power minus mod x will be half of e to the power minus x, because in that case x is greater than 0 and mod x is x itself. The random variable of the problem is of continuous nature, which we are pretty sure by looking into the structure of the probability density function. Hence, the moment generating function of the random variable is therefore given as, why am I writing this line? Because I am ensuring that whether I'm going to apply the summation sign or integration sign. And since this is of continuous nature, I'm going to apply the integration sign. So I'm writing it minus infinity to infinity e to the power tx fx dx. Now you replace your fx. In this range, minus infinity to 0, your fx is half e to the power minus minus x. And in this range, 0 to infinity, your function is half e to the power minus x. Then what? Then we are going to actually integrating the things, but before that I have done something. I have taken out the constant half outside the integration sign. Okay, so I'm writing it as minus infinity to 0 e to the power tx e to the power minus minus x, which will be e to the power just e to the power x only, and that will be e to the power tx into e to the power minus x. So if you integrate these two, you are going to get this result. Verify. E to the power t plus 1 x by t plus 1 ranges from minus infinity to 0, and e to the power t minus 1 x by t minus 1 ranges from 0 to infinity. Now I am putting the limits. Now you see, carefully observe. First of all, I am putting x equal to 0, upper limit. So that will be e to the power 0 by t plus 1. So I am writing 1 by t plus 1. And when I am putting minus infinity here, so I am going to get something as e to the power minus infinity. You take it below in the denominator, and that thing will vanish. 1 by infinity is undefined. It vanishes. It is equivalent to 0. So the second term is vanishing. What happens for the second integrand? I am showing it explicitly for the sake of your understanding. I am putting the upper limit as infinity and lower limit as 0. Observe carefully. Then, since you will say that, okay, see, here's our infinity is plus, so in the numerator plus infinity will be there. So infinity minus something, absurdity, looks like absurdity, so result will not come out. So I am doing a mathematical trick here. What I am doing to erase this particular absurdity, I am writing tactfully t minus 1 as 1 minus t. And if I do so, infinity will become minus infinity. Okay, I'm taking minus 1 outside, common. So now it becomes minus infinity. And instantly, this e to the power minus infinity goes to the denominator and it vanishes. This vanishes. And therefore, I'm ultimately going to get half 1 by t plus 1 minus half 1 by t minus 1. And therefore, ultimately, if you simplify, you are going to get it as 1 by 1 minus t square. So we have proved that for some random continuous random variable x, if this is the probability density function, then its moment generating function will be of the form 1 by 1 minus t square. One thing I have not shown over here, but you can do by yourself, okay, that since you know the moment generating function of this particular random variable, you can take the derivative of that. You can put t equal to 0. You can find its mean. You can find its variance. Okay, so moment generating function is a very powerful observation, and it helps us to identify the mean and variance, these statistical parameters for any random variable, whether discrete or continuous. So whenever next time you will be doing signal systems, and whenever we are going to get the signals in the form of some probabilities, Nyquist theorem, okay? So you are going to get this as probabilities, and if these probabilities are unknown, that means the signal is unknown to you. Okay, you are to study the signal. What you will do, you will find the, first of all, you will try to derive, the signals are digital, so these are you are doing digital signal processing, so that that will be discrete. So you are going to, you will try to derive a discrete, you will try to derive the probability mass function. If you are doing the continuous signal processing, you will try to derive the continuous probability density function. And once you can identify the probability mass function or probability density function to get the average number of signals coming in with some probabilities, okay, you can find the moment generating function of that probability and find out the mean as well as variance. So this is the trump card which I'm showing you in today's class, and you can correlate my today's this thing to your signal systems. You can scan through the books and you can verify whether I'm right or wrong. In signal system book, there is a chapter called sampling distribution. You go to the chapter directly and just look for yourself. Okay, so this much for today. My time is already running out. Tomorrow we are going to meet with some new topic, and if you have any doubts, you can ask me at any time through WhatsApp. So till then, goodbye, see you tomorrow.
Thank you,
Thank you,
sir.
sir. Thank you, sir.